So during the last meeting, we had covered value iteration for stochastic games. And this was an exact solution technique. And really, like the first algorithm we looked at that uses the concepts of game theory to solve not just a non-repeated game like we had looked at before, where you just have a single game state, like rock, paper, scissors was an example of that. But now we're talking about stochastic games where there are multiple states. And the point of this algorithm, it's kind of summarized pretty well in these two steps here, where we go through the state space twice in alternating sweeps until this process converges. And actually, the second sweep will just go through the state space like we do in normal value iteration. This sweep, the first one, and the reason why this takes quite a bit longer than value iteration, is because this actually has to sweep through all of the states, agents, and joint actions. So there's quite a bit more that has to be calculated here. And the first sweep is calculating these M values. And these are, a unique value for every state, agent, and joint action. But the point of these values is it is supposed to take, once you slice this in terms of the states and agents, look at the joint actions. If it's a two-player game, then the joint action space is two-dimensional. There's one action for each of the agents. And that would make this a matrix, or the joint action space, you can index it like a matrix. And then each of these matrices, each of these slices, you can actually view it as if it's a normal form game in that state, because the values of the matrix here are supposed to account for, like normally in a normal form game, there's this reward matrix, which tells you what are the reward values each agent gets for every joint action selection. But in a stochastic game, you can also transition into other states. So now these M values are going to account not just for, and you can see it written out here kind of explicitly in this recursive form, but this is accounting for the immediate reward that the stochastic game provides, and also the discounted value of all of the transition states that you end up in. But once this converges and these values are correct, then we can think of each state as if it's equivalent to a normal form game, but where the reward values now, instead of just the immediate reward values, are constituted by these M values. And then these M values, when they are converged, are going to depend on also all of the state values. And the state values, both of these will be self-consistent when it converges, where then whatever game solution concept we apply to the equivalent game in that state will then be the state values that are then also consistent with all of the, the game discounted values that we try to calculate, accounting for all these possible transitions. Were there any questions about this this value iteration algorithm? I know that this also builds upon a lot of game theory concepts we had covered previously, so you might have to review that material. But I'll show a concrete example of this with the specific game that we looked at for the solution, which was this soccer game. Actually, I'll leave this on here for now. So we had looked at this soccer game example last time, and we're going to keep using it for some new algorithms that we look at. And so this soccer game, this is a zero-sum game, right? So there's only two agents, and each agent in this case actually has, wait here, I'll go back. Let me show here. I don't actually have it here. I'll just show what this soccer game actually looks like here. So this is defined somewhere else. But here, so it's a stochastic game, and here are the agent actions. So this is like each agent has 5 actions available. So it's the 4 normal directions, and then there's this no-op action, which is for when the agents choose to just stay still, not do anything. And the rules of the game are very simple. So here I'm displaying the game where the filled-in circle is the agent that currently has the ball. So when the agents move, they just carry the ball with them. And both players move, like on each turn, both players will simultaneously select an action. And normally that just means they just move to their desired position on the field. If an agent with the ball moves into their corresponding goal, then they get a reward of 1, and then the episode ends. And this is also a discounted task, so there's a discount rate, so that incentivizes the player to try to win within a finite number of time steps, because otherwise the reward they get is effectively 0 if they stall the game for an infinite amount of time. And the ball can change hands in the case where the 2 agents collide. So if 2 agents try to move and at some point in that process they occupy the same position on the grid, then the agent that attempted to move in to where a grid was already occupied, they lose the ball if they have the ball. And there is some randomness here because this process, this is decided based on which agent got to move first, which is a random factor in the game. So, practically, like, these agents actually move, they move simultaneously, right? But for the purpose of calculating if, which player loses the ball in the case of a collision, there is some random coin flip where it'll be decided where, if one player was attempting to move first and the other agent has yet to move, so then they would be considered the agent trying to encroach on the space and they would lose the ball. Okay, so because this is a zero-sum game, we can apply the minimax solution concept to this, right? So for all zero-sum games zero-sum games are always 2-player games. There is this unique minimax solution in which both players' policies are an optimal or a best possible response to the other player's policies. And that is occurring simultaneously. So basically both players are stuck in this policy where neither one can make a change that would result in any kind of improvement to their policy. So that's why when we see this value iteration has solved for the minimax solution in this game, and it results in a win rate of 50% because this reward value is effectively 0. We see a slight negative value here, but actually if we repeat this computation, we'll see that this will go from being a slight positive number to a slight negative number because it's within the numerical noise of this averaging. And the minimax solution in this game happened to be one where we can sort of segment it between whether the player starts with the ball, which can occur randomly. So for the player that starts with the ball, they have a 2/3 chance of winning and a 1/3 chance of losing. And same, if they start without the ball, it's reversed. And then the episodes on average take, 13.6 steps on average. So this is what, the solution looks like if we actually show an episode play out. So what happens is, and I did show this last time, but the players, so the player with the ball will now attempt to move and score, and then they get locked into this position and they end up eventually positioning themselves. So far there's been no risk of the balls colliding or anything, but these minimax solutions always structure themselves so that the one agent is in a position to score, and then the other agent positions itself in a position to steal the ball back. But of course, there's a risk here. So basically, there's a 50% chance of this working, and if not, the agent will score. And all the moves prior to that are just jockeying and positioning until they get into this point. But this strategy ends up producing this, 2/3 win rate for the player that starts with the ball, because then they have a chance to steal back after this point if they lose it. And also, this is the policy that results in this average reward of 0 between the 2 agents. So we'll see here that in this case, because of the way the coin flip worked, this player was, permitted to move first into here, even though we can see from the actions they're both trying to go into the same square. So here A succeeded, and therefore then scores and wins in this short time. Now what I'm showing here on this side is the actual minimax policy, like the actual probabilities. And here, it's showing the actual action that was selected. But what this means is that in this particular state, player A, which is the blue player, has this policy where they have, a 50% chance of taking the up action and a 50% chance of staying still. And B sort of has the same thing. That this left action effectively is just staying still because B can't actually, enter the goal here without the ball. And if we go back a little, there was, like, here's another example where when they're just facing each other like this, player A, it has this policy where there's a chance of going down and also a chance of staying still. And similarly, B has a chance of going left and a chance of going down. So this game in general has, like the equilibrium minimax solution is a probabilistic solution. So in order for this minimax solution to work, where there's no way to exploit it, it requires, both players to have these random chances in the policy space. And then also these grid values here, you see, these are the slices, like these M matrices. This is what the solution is, where now each state here, this grid, where this 5x5 grid, this is what is treating each game state in the soccer game as an effective normal form game in that state. So like if we actually wrote a normal form game where these were the reward values, like a non-repeated game, then these would be the minimax policy solutions for this game. And that's what our goal is for all these stochastic games, is to take the state space and, we're trying to come up with a solution that only depends on the current state we're in, if it's an equilibrium solution, and it will reduce the stochastic game so that we can think of it as just a series of normal form games that we can just evaluate each one, separately. Of course, all the states are interconnected by the value function that we solve for right here, but by these values, but they summarize all the information about the future states. Okay, so any questions about the minimax solution for the soccer game? That's good. And here I'm just showing them playing against each other. So we can also evaluate the minimax solution against a random opponent, and this will be something we're going to evaluate. Look at other solution strategies and see how it performs against random opponents. And we can see that it does pretty well against the random opponent, winning 98.2% of the time. This is like the actual score, like the thing that would be maximized if we were to try to, do as well as possible in this game, would be not the win rate, but the actual reward value here, the expected discounted reward for the agent. So here we could see it as a value of 0.385. Remember, you get a reward of 1 for winning the game, and then there's a discount rate in this problem of 0.9. So every step into the future you get a reward, it gets multiplied by another factor of 0.9. So there's exponentially decaying rewards. But for the random opponent, it looks like when we start with the ball, we have nearly 100% win rate, and with only 5 steps. So a 5-step win would be a situation where we start with the ball and we just move directly to the goal and nothing blocks us. So we could see that there's some small amount of time when it's not that clean and there's something in the way. And then when we start without the ball, the win rate is lower and it takes many more steps to win. So the overall discounted reward is a combination of the half of the time when we start with the ball and the half when we start without the ball. And so now we can see an example of a game where now the first opponent, so player A is the minimax player and player B is the random opponent. So we can see player B is going to always be just making random moves. We can see, of course, player A now is not playing like it's still playing with the minimax policy, which means it's assuming its opponent is also optimal. And yet, of course, this is still going to succeed against any opponent that's less than optimal. So we can see what our player. So remember, the blue player is the one that is the optimal player in this case, and it's still, it's playing very conservatively. It's positioning itself like as if its opponent is an optimal player. But we can see what's going to happen here. So this is the case where if player B was optimal, A would be trying to steal the ball here. And actually, randomly, that is what happens. But then normally, then B would just win this game because they would just go into the goal. But we can see because B is random, A sort of gave up, but now realizes it actually has a chance to fix, what it thought was a completely lost game. And eventually here, right, this is a case where A, its policy actually is to split its actions between all of this, which is kind of complicated. B also has a complicated policy, but there is a chance here if B goes up, which in fact B does go up here, that it steals the ball and then it just goes and scores immediately, right? But because against the minimax opponent, A does set up the situation where it does incur some risk. It tries to score, which in turn exposes it to losing the ball. So that's why there is some small percent of the time when it actually loses to a random opponent. We'd have to train this in a different way if we wanted to win and incur zero risk of ever losing one of the episodes. So, okay. So this is against a random opponent. So now we're going to look at is something where we can learn through sampling instead of an exact solution. So this algorithm in this step, notice how this T function, this is the probability transition function for the game. And this tells us all the probabilities of after a joint action is selected, what the state transitions are. Now, if we don't have access to this, then we can't perform this step of the calculation. And that's where this next type of learning comes in, where we're going to do temporal difference learning, which we did with single agent RL. But now in the context of joint actions, and this is the update step. Now, this would be for an exact solution like we had with value iteration, where here we're summing over the probabilities. But the idea behind this algorithm is that we're going to take samples of this by having two agents play in an environment and observing the rewards and observing from the actions that the agents select what states they end up in. And therefore, we're going to learn these joint action values, which are the analog of the M values we had here, right? But now instead of learning these state values, we're going to use these, sampled versions of the Q values the whole way, where we're also explicitly using the probabilities here from the policies of the other agents, which we can also sample from. So this is something we can sample from, right? Because we're going to actually have a version of the agents interacting with each other and with the environment, and we can sample from this. And that's what this algorithm does. So we initialize everything, and what we start in these states, and then we actually choose actions in the environment. We have this factor of epsilon again, like we have with ordinary reinforcement learning, where we have a chance, right, of choosing random actions, and this allows us to guarantee that we explore the environment, even, these, like prior to actually converging to the correct values, these policies could get stuck in things where they just repeat the same actions over and over, and we need to break that somehow with this exploration factor for probabilities. But then we have these values, right? This is like the slice of the equivalent normal form game in the state, where here instead of the M values, these are the Q values that we're learning, right, for the joint actions and for the particular state we're interested in. And then just like before, we treat this as a normal form game, and we apply this value step, where here we apply the game theory solution concept. Like in the soccer game, this would be calculating the minimax value, which we did with a linear program. But like we saw in a previous chapter how we could use a linear program to calculate the minimax value once we have these correct game values, right? So this is just a standard temporal difference update. This is the game theory part of it. And then this is where we actually use the game theory solution to get the policies, prior to where they've converged. These are not going to be exactly correct, but we're going to use them to take samples. And hopefully, over time, as long as we decrease the learning rate and, decrease epsilon over time, this should converge in certain classes of games. So here's the code. So here's the step where this is the version of the algorithm that works for a minimax game, right? This is where the way I've written this code, these games have a type parameter in them, which tells you like what type of game it is. So here, this is for a zero-sum game, meaning that there's just one reward value. It's positive for one player, negative for the other player. That's what makes it a zero-sum game. And for zero-sum games, we actually only need one set of the Q values, because they're always going to be like one set of values is going to be the negative of the other. So we don't need to actually store multiple sets of values, because it would just be redundant. We can just take note of which player we're talking about and then just multiply it by -1 if we're talking about the second player. So yeah, this solve minimax game also occurs in the value iteration algorithm, but here it's different because we are instantiating the episode. Like we start with an initial state index here, and then we go through and actually sample actions. Here there's only 2 players to worry about, and then on every step of the algorithm we have to solve the game in the state we're in order to derive the policy from the Q values, right? Just like we did. So we're always deriving the equilibrium policy from the joint action values in these algorithms. So we can see now what this looks like with the soccer game. So here now we have to actually say like how many training steps we want to go through. And then we have learning rates here. This is being trained just based on what it says in the book to actually decay the learning rate over time. And then the result of this, of running this algorithm, is that now we have all these joint action values, right? And these values are the equivalent, the slices of the game that are shown here. And then the policies, probabilities here are derived from these joint action values. And we can see, so this would be called like a minimax Q solution, Q for actually that we're sampling the joint action values. And we can see that this hasn't quite, converged. Like unlike the exact solution, this should be like 50% and the value should be 0. And if we keep doing this, we can see that, this hasn't learned a perfect solution because, again, we're sampling now. And we can see what the solution looks like. So actually what this does is that the lower part of this is the minimax Q values and the corresponding policy solution. And we can find maybe a state where these values don't match. So here it's actually pretty close. But we can see like in this game, the exact solution, it has pretty precise values. Like here, the player A policy, even though this matches where the probability is split between the up and the right action, we can see the minimax solution is 0.341 and 0.659. And here, because of our sampling error, we've learned different probabilities. And, this hopefully wouldn't cause too big of a problem. At least the actual, which actions exist in here match. But these probabilities are different. So in theory, like this policy could be exploited in some way because it's not the exact values. If we go on, now we can see other instances, right, where now these values, again, these probabilities are not matching. At least, the actions are still matching. And here's a case where it doesn't matter because both of the policies are deterministic. Now, if we actually play this, okay, so here's, again, playing against a random opponent. And we can see, if we compare it to the other one where it was like a 98, 99% win rate, We can see now this is less successful against a random opponent, but it's still pretty good. The value here is 0.354. What did we have before? It was 0.387. So we can see like the true minimax policy does better against a random opponent than this one does. The other comparison we can make is we can play the minimax Q directly against the minimax opponent, and it should lose, right? Like it shouldn't be as good. We can see instead of a 50% win rate, it has a 40% win rate, and it does have a negative value here, indicating that it is a worse policy overall. And this is what we would expect, because this random sampling is not going to converge as well to the exact solution. I guess I already. But yeah, so in this case, the A player is the approximate solution, and the B player is the exact solution. So here's a case where B was able to win the game, although I think in this case B wins the game by just doing the normal. Yeah, like this is the same situation we would have with the two minimax opponents against each other, right? Where it sets up this steal opportunity, and then it just happened to win the coin flip. We do see here a difference between the two policies, where here the A player ideally should either go down or to the left in this situation, but what it actually does is stays still, which, well, yeah, I'm not sure. I guess I'm not sure if this actually makes too much of a difference for the success of the policy. But again, like it does try to steal here, but of course, whenever this situation is set up where it tries to steal, if it fails, then it always guarantees the opponent can score a goal, because at that point, the opponent will be past it here. Like what happens here, it gets past it, and now A doesn't have any way of stopping B from scoring. Yeah, so any questions about the minimax Q versus minimax? The basic overview idea is just that when you have to learn from random sampling, you're not going to get as precise of a solution. And for this soccer game, at least, the book only shows all these results in the book are based on minimax Q, not the actual like exact solution. But this soccer game is one where you can write it down in a way where you can actually get an exact solution, because we do know all the probabilities for the game. Okay. Now this, I didn't show this for the minimax solution, the exact one, but if we go, this rock, paper, scissors game is going to come up in some future algorithms, but this is a game where the payoff matrix for this game is this 3x3 matrix, right? Where on the diagonal, the value is 0. Those are cases where you tie, you both pick the same action. And then every row has an action that loses and an action that wins, right? This is just how rock, paper, scissors works. And this is just a normal form game, right? We can always write it down as a stochastic game, because then it'll work easily with all these algorithms that we already have. But to make it a stochastic game, we just need to create two states where there's a play state and a terminal state. And the play state is the one where we have the rock, paper, scissors reward values. And then the terminal state is just the values are all 0. And so this effectively is just a trivial stochastic game where we always play in the same state over and over again. But then if we apply this joint action value learning, what should happen is that the learned values should converge to the true values. Here, we, like normally with the stochastic game, we don't know the true values because it depends on all the future states. But because this is a trivial example, the only rewards that matter are the ones we get from the play state. So here we could see these values have basically, converged after 500 steps. And right, I mean, not exactly, like these values should be 1, but it doesn't really affect the policy too much. And then if we solve this minimax game with the, linear programming, we get a minimax solution where all the probabilities are equally, each player chooses with uniformly random probabilities. That's the minimax solution. We can see, because these values aren't exactly the same, like this should be -1 and 1, these probabilities aren't exactly 1/3, and that's where you see where this random sampling can be a problem. So if you have games where the equilibrium solution really does depend on these precise probabilities, then, it's going to perform suboptimally. Because in order for these values to truly be 1/3, all of them, this has to be completely converged to, where these are all, this is -1 and 1. This is 1, -1. So that's just to show that, these policies are computed with that linear program from the learned joint action values. So, and if we were to solve this game with the true values of the rock, paper, scissors game, these values would all be 1/3. All right, this is just showing the package I'm using for linear programming to solve, an arbitrary matrix game, minimax game in this case. Okay, does this make sense to everyone? We do the sampling, get the equilibrium solution, but with minimax Q, it's not, right? We're not going to get the exact solution. We're just, okay. So there is this other note here we can touch on. So far I've only talked about minimax Q. Now you could apply other equilibrium game solution concepts to this, like Nash Q learning, in which case we would just learn joint action values for each agent, and then we would try to compute the Nash equilibrium solution for a general sum game, which unfortunately there's no general way of doing this. We can verify a Nash equilibrium solution. There's also a note here about, actually, I don't know if it mentions all the conditions, but for this, so first of all, like we have to have an algorithm that actually can compute the Nash equilibrium, which is already difficult in the general case. And then even if we have that, it's not guaranteed to converge. The actual, sampling process we use in Q-learning is not guaranteed to converge to the Nash equilibrium. And there's a note here that whatever the condition is that needs to exist, it has to apply to all of the game states, like all of the equivalent normal form games in every game state. So that's pretty unlikely. So there's a lot of different problems with this, which is why there's no, pseudocode for it in the book. And I did not write an implementation of this because there's no way to guarantee that it will work. The other thing we talked about earlier was correlated equilibria, which do exist. We can compute correlated equilibria with a linear program that was mentioned in an earlier chapter. But we do have to add a constraint like that we want it to be Pareto optimal or something, because there could be an infinite number of these correlated equilibria. So we add some other condition to it. But the problem with this is that this here, no formal conditions are known under which correlated Q-learning converges to a correlated equilibrium of a stochastic game. So that is, another problem with this is that, we don't actually know if this will converge in the first place. So another thing that maybe sounds like a good idea, but practically probably won't work. So the most straightforward thing to apply this joint action learning to is the minimax game, because that's one where we know there's a unique equilibrium. It will actually converge to it, and we actually can write down a linear program that can calculate, the minimax solution. So now there is this section here, which I think is worth going through, which talks about the limitations of joint action learning. So recall that for these algorithms, if I show the soccer game, the way all these algorithms work is we're trying to learn these joint action values and reduce the game to something which is equivalent to a normal form game. And then we always derive the policy, right, from the action values. Okay, so just keep that in mind. Now, the action values, are conditioned on the state only, right? I mean, also on the joint actions, but yeah, like we have values for the joint actions. But other than the joint actions, they're conditioned on the state. They're not conditioned on any kind of history of the states or the policies. So that means that whatever the equilibrium policy is that we derive from these is also only going to be conditioned on the state. Now, if you recall in ordinary reinforcement learning, when we learn the action values, or not the joint action values, but just for a single agent, when we compute the optimal policy, we take the argmax of this, where we're trying to find the action that produces the highest value. And that results in a deterministic policy, or at least one that, the optimal solution could be a deterministic policy. We could also choose with arbitrary probabilities among all of the equally good actions, but, we're always free to make it deterministic by just choosing the first action that shows up, which is an argmax of this Q function. Now, the problem is we know that when we have these normal form games, like an arbitrary one, the equilibrium solution could be stochastic, right? And when we solve this, when we have a matrix like this and we solve it, we in general will get, stochastic solutions. It could be deterministic, where there's just a 1 probability for one action, but it could also be stochastic. And when we look at action value learning, when it's not a matrix, like in the case where normal reinforcement learning, we just have, a list of action values. There's just a value for every single action that one agent can make. There is no other agent to worry about. Then those solutions are not stochastic like this. They can't compute some kind of arbitrary, probability between two actions. So the book brings up this point that, let's say we have a game where the agents alternate taking turns. So in any given state, only one of the agents is making action selections, and the other agent effectively has only one action, which is to do nothing. Now, in this case, the joint action value function we have, is just going to be either a row vector or a column vector, right, where the other agent doesn't have any action selection. And this actually reduces the problem to what we would have in single agent RL, where we just pick the argmax from the Q function, and we can't compute these. The only reason why this can compute probabilistic policies is because both agents have multiple actions. Therefore, both agents have to consider all of the different responses that the other agent could make at the same time. But if you imagine a game like tic-tac-toe, that's a game or chess, where the two players alternate making moves. So if we do some kind of joint action learning, it will effectively just be a single agent action value function for every state, because only one agent is actually, has action selection. So you're going to end up with deterministic solutions in that case. which could be fine. So then the question becomes, okay, so if we have a turn-taking game like this, where, only one agent can make decisions in any state, are there situations where a game like this has probabilistic equilibrium solutions? Because if that is true, then it means a joint action method cannot learn that solution, right? Because it will end up only being able to learn solutions that maximize the action values for the agent in that state. And it turns out there is a game like that, which was written in this paper in 2005. And the game looks like this. So it has two states. And in the first state, the agent 1 chooses actions. And in the second state, agent 2 chooses actions, right? Now they have the same actions available in corresponding state. They can either send or keep. So keep will keep the game in the current state and produce either this reward or this reward. And then the send action will send the game into the other state with this reward. So this game, if we look at just the deterministic policies, because each agent can only make an action selection in one state. So there are only 4 deterministic joint policies for this game. And I will show them. There's different ways of writing it down, but let me just show it here. So like deterministic means, like the policy can only depend on the state, right? And the agent can only make an action selection in one state. So, and there's only 2 actions available. So the 4 possible deterministic policies are send, keep, send, keep, and keep. Okay, so we can look at what the situation is for each of these. So let's say we look at send. Okay, so what does that mean? Well, it means if we start here, then it's going to produce this reward. Then it's going to go to state 2. Then it's going to produce this reward back in state 1. And then this will repeat forever. So that's what I'm showing here. It's going to produce this reward sequence, right? 0, 3, 0, 0, 0, 3, 0, 0. Or if we start in state 2, it will be 0, 0, 0, 3, 0, 0, 0, 3, and then, repeating forever. And we can calculate the discounted value here. The book says the authors selected this discount rate of 3/4 in this case. So this will produce this infinite sum of rewards, right? For agent 1, it's just a reward of 0. And for agent 2, it's, 3, 0, and it's going to be 3 plus 0 plus 3 times gamma squared plus 0 plus 3 times gamma to the 4th, etc. And that just produces this value. And similarly here, this is a lower value because the reward is shifted 1 step into the future here. Okay, so now, so we have apparently what the values are for the different scenarios for the 2 agents when they follow this joint policy, send. And for each of these, we can ask, is this deterministic joint policy an equilibrium solution? And the answer is no for all of them. And the reason is, if we keep going through and here I've evaluated the values for all of them, right? So we have keep, send. If we look at keep, send, keep will just produce this reward of 1, 0 over and over if we start here. And then if we start in S2, because agent 2 chooses the send action, then what will happen is we'll first get this reward, and then it will produce this forever. And then we can also look at send keep, which goes the other way, where, we send, we produce this reward, and then on the first step, and then this reward over and over again. Or it just stays at this reward indefinitely. And then finally, we have the keep action, which depending on which state you start in, will just produce, this reward sequence over and over. Okay, so here we can compute, here are the values for both agents for all the different policies. And by doing this, we can see that none of these are equilibrium solutions. So if we look at this one, we have these values. So agent one's expected reward is 0. Now, if agent one switches to the keep action, then it changes this from send to keep send, which is number 2. And if we look at keep send, agent one has higher reward values, right? So in this case, agent one can improve the situation here by switching its action to keep. And similarly, if we look here, now agent two has a reward of 0 in both starting states. If it switches its action to keep, then we're in scenario 4, where now, even though this reward is 0, the reward it gets here is 4, and this is a better outcome, right? So agent 2 benefits from switching its action. Here, we have these values. If agent 2 switches to send, it results in send, which is the first one we calculated. And these two values we can see are both higher than these two values, right? 6 and 4 versus 6.857 and 5.14. And then for the last one, if agent 1 switches to send, then we have send keep, which is this. And we can see that it produces a higher value rate, 9 and 12 versus 4 and 12. So it had made an improvement in this starting state. Okay, so none of these are equilibrium solutions. However, we know that for this game, there is an equilibrium solution. It just happens to be a probabilistic one. You'd have to look at the paper to see exactly how they compute it, but apparently agent 1 choosing the send action 2/3 of the time, and agent 2 choosing the send action 5/12 of the time is a probabilistic equilibrium for this stochastic game. But we know that the joint actions we learn would never be able to reproduce this, because the joint action function is just going to be a vector in every state. It's not going to be a matrix. So we have no way of learning these probabilistic equilibrium values. And there's this theorem mentioned in the book that says that if we have two different games and they could have different equilibrium policies, but they could share the same joint action function. And that means that the joint action function is never going to be able to derive, we can never derive from it the true equilibrium policy solution in the case of games like this. I believe so. This problem should only exist in games where there are states in the game where one of the players doesn't have any action choice to make, because that will always produce a situation where the joint action values are just one-dimensional, and therefore they cannot learn a probabilistic equilibrium. So that is, so far we haven't looked at a game like that, like a real example. There's just this toy example here. But it does create a limitation for these algorithms that, you could certainly encounter a game where even some of the states meet that criteria. And then that would be a problem, because we would need an additional technique besides joint action values to learn the equilibrium there. So any questions about this? And this they call this game no STE, for no stationary deterministic equilibrium, because the only stationary equilibrium is a probabilistic one, not a deterministic one. Okay, so if you recall, in the last chapter, we looked at algorithms that didn't use game theory concepts. One of them was independent Q learning. And this was where we just took the agents, we gave each agent its own Q function, and asked it to act as if it was an agent learning in an environment, without accounting for the behavior of the other agent. So it just samples from the environment, and it treats the other agents as part of the environment. Now, the fact that they're changing over time causes problems because it can result in this algorithm not converging. Also, this can't learn probabilistic equilibria either, for the same reason as what I just said about the action values being vectors. So we can still apply it. Now, in the case of the soccer game, we have the zero-sum soccer game. Independent Q learning shouldn't really converge in this case because as it's converging, one player should eventually be able to exploit the other. Now, but practically, it's unclear exactly what's going to happen if we do this. We can see here's a result of the reward for player A as this process goes on. So it does sort of converge to something where these values now are very small. But we can see that the win rate here, the average reward over time should go to 0 if it actually learns the true minimax solution, which is probabilistic. This can't really do that. The agents could still get locked in to something where they do learn, they do get into some kind of cyclical equilibrium where they alternate over time. And that could be happening here. But we can see what, at the end of this process, it did apparently, learn something where they're at a 50% win rate. It's not exactly like the minimax solution though, because if I keep running this, I believe this value is always negative, slightly negative. Whereas, so this is not really just numerical noise. Like this is truly, even after 10 million steps, it's converged to something where the first player does, lose on a very slight but consistent basis. And also these win-lose probabilities aren't matching exactly. But we can still see what the solution looks like. Again, these are all going to be deterministic policies, unlike the minimax one, where these play against each other. But it is going to end up looking about the same. But again, their behavior is going to alternate. Instead of, in the minimax solution, it might be a case where player A here, either goes up or left, or either stays still or goes up. And here it's learned, and B is sort of locked into, its own policy where it knows that player A is going to do this, but they're sort of in a stalemate. But in this case, a deterministic stalemate. But they're still going to create the scenario where here, this is the same scenario we see for the minimax solution, where one player positions itself to try to steal, and then if it loses the coin flip, it just loses the game. But, they're going to end up getting into that same sort of position, but we'll see how these policies are different from the game theory ones when we actually play them against each other. The other thing to note is that this solution that it's learned, this deterministic one, actually does better against the random opponent than the minimax solution. You can see it has a higher value here. I think the minimax was 0.38. This is 0.43. It also has a higher overall win rate. And we can see it also does pretty well against the minimax opponent. This is the actual converged minimax opponent. But we can see this slight negative value means it does consistently lose to it. But it's still, it's still performing pretty well. Because again, the minimax opponent is not trying to exploit this, independent Q learning policy. It's just, assuming its own opponent is optimal. And again, against the imperfect Q, the minimax Q, which learns from sampling, is not exact, it does even better. But, one thing we can do to compare all these solutions is we can compare them to optimal opponents. So this would be a situation where we have the policy, and then we put it in a situation where some algorithm is going to look at it and try to learn the best way to exploit it. And this is important when we think about the minimax solution, because the whole point of the minimax solution is that it's this equilibrium where if both players follow it, there can be no improvement by making a change. And that means that there is no change that a player could make to have a better performance against it. So even if we train an opponent specifically against the minimax solution, it shouldn't produce any success. However, any other opponent that would not be the case. Also, the minimax solution is unique. So there should only be one unique policy that has that property, or we can't exploit it in any way. So we can do this in different ways. In the book, they have this chart where they talk about it with the soccer game. And I think they just use independent Q-learning to train the optimal opponent. So I have the option to do that here. Let's see. So when I wrote this independent Q-learning algorithm, there's this flag in here that I added for train policies, where by default, it will train all the policies simultaneously. But if you want, you could just say, throw the policies in there together, fix all of them except one. Then this algorithm will reduce to just ordinary Q-learning, where all of the other policies are fixed. They actually form an MDP environment because they're not changing over time. And then that's something we could perform Q-learning on. The other thing that we can do is, if we actually know the policies of the other agents, like explicitly, then we can instantiate like an MDP where we actually know all the probabilities. And then we could apply an exact solution technique to it. And I do both here. So this is an example of doing independent Q-learning against a random opponent. So here so the policies always start out random when we do this. That's like the initial policy that we start with, because all the action values are equal. And then here, I'm only going to train the second policy. So there's two agents. One is going to stay random. The other is going to train. And here, this is the learning curve over time for the A player. So the A player is the one that's not learning. So it is doing worse and worse over time as the opponent learns to exploit it. So this is an example of saying, we know we have a random opponent. What is the policy that best exploits a random opponent? And the other thing we can do is, so I added this utility to this notebook, but the way it actually works is that we form an MDP for the soccer game with a random opponent. So now this is no longer a stochastic game. Now this is a tabular, Markov decision process where the random policy is filling in, the missing information about the other agent. And now we can see, normally in the soccer game, all the transitions would be either deterministic, or there'd be a probability of 0.5 for the coin flip when the players collide. In this case, now we can see the probabilities are split between 5 different outcomes because of the random policy, the random opponent. So all we have to do is go through, and we can just iterate through all the probabilities of the policy, form this MDP, and now we can actually solve for, using an exact solution method, the optimal policy against this opponent. And that's what's being done here. It forms the MDP of the soccer game. It uses value iteration, gets the optimal policy. And here is the result, the statistics. Now, in this case, the Q-learning works pretty well too. The result for the exact solution is a little better, right? But this reward value, right, this is a better outcome than any of the other policies we had, right? Where with independent Q-learning, we had like negative 0.4, and here we have negative 0.5. So this value here is the best that you could do, with this discount rate of 0.9 in this game against a random opponent. And we can see that we win with an average of 7.32 steps. So the win rate for the random opponent is 0.0077, right? So 1 minus that is the win rate for the optimal opponent. And we can see what it looks like. It will, again, look very different from the policies we've seen so far, because so far we've never, tried to tailor something specifically against a random opponent. So we can see what it looks like here. So this is a case where the first player A is random, right? And player B is the perfect opponent. So we can see what it tries to do. It's A. So A is just moving around randomly. And what the optimal opponent tries to do is it just tries to position itself as close as possible to this player. And here it's going to move and attempt to just back it into a corner. And now it's in a situation where, it's not going to be perfect, right? It doesn't know if A is going to move this way or down. Here it happens to move down, but, this also blocks it from reaching the goal. And here now it steals the ball, and now it's in a position to score in just one step. And we could generate a new episode of this and see what it does. Let's see if we can get one with more steps. So here's a case where B now starts with the ball. When B starts with the ball, because the opponent's random, it doesn't try to do anything safe. It just marches straight for the goal. It doesn't care if A tries to block it or anything, because the most likely outcome is that A doesn't block it, and it goes. So this will win in 4 steps. We can see when it starts with the ball, right, it wins in an average of 4.63 steps. So 4 steps is when there's no interruption. You can see if we can get, if any of these end up being longer games. So here's so this is kind of a random case where this ended up being a 23 step game. I'm not sure why. We could see it probably just takes a while, where now B is trying to just position itself as close as A as possible, but A is kind of running away, and then it just waits here for a while. And this is this many steps because, right, now here, normally against a good opponent, right, this would be horrible because now it can just walk in and win, but B doesn't, you would think A would win here, right? But actually, because it's random, it just wastes time, and then B still is positioning itself right in front, moving into A because of that coin flip chance of getting the ball. And then once it has the ball, it just moves in the other direction and scores. So that is what, the optimal policy against a random opponent looks like. You just sort of crowd into the opponent and try to, get as many opportunities as possible to collide with it. Because you know that by colliding, you're going to get the ball. And then once you have the ball, A is very unlikely to be able to stop you. Now we can do the same exact thing with the minimax opponent, right? So here we're going to learn the optimal opponent to this was the minimax player. And we can see here that we have this. Now, again, what the minimax opponent does is it makes it so you can't get net positive reward. Now, in this case, the win rate is actually slightly above 0.5, but we can see the reward value here is slightly negative. And if we run this multiple times, we'll see that this value, again, is essentially 0. It's negative now, but I think with numerical noise, it will, here it's a slightly positive value, but this value is just within the numerical noise of 0. So this proves that the minimax opponent, right, we can't exploit it because the best we can do against it, it's this solution, but the reward is 0. And we can see what the opponent looks like. I think practically, so player B again is the optimal opponent, and its probabilities, we're going to see some of them are split, but these are always going to be even splits of probability because we're learning what is a deterministic policy or deterministic where there's even probabilities split between all of the equally optimal actions. So we could just choose one of these and it would be equally optimal to splitting the probability in some other way. But I believe what player B does is it practically its solution ends up looking like the minimax solution, but where we just sort of only ended up picking one of the actions instead of 2 of them. Here, this is the minimax policy, so it's up and right, but the up probability is 0.8. And here for the optimal thing we did, which is deterministic, we basically just, choose one of these up or right, but there's no special, probability split between them. But otherwise it should look the same. And the actual statistics of this in terms of the reward should be the same as the minimax opponent. The win rate is a little different because it's not the same policy again, but it has the same outcome in terms of 0 net reward. Now, again, with the minimax Q-learning, this is where we did joint action learning with sampling. And here we can see the optimal opponent is successful, right? Where now we've tanked. Our minimax Q is only winning a quarter of the time, and the reward is negative 0.2. So this is successful, and the reason is because this is learning through random sampling. So there are blind spots. We can actually see where the blind spots are by looking at an example episode. So here, B is the optimal opponent. A is the joint action learning policy. So we can see that weirdly, B does something which we would never expect a normal opponent to do, which is it moves to the left. So like, why does here, B is trying to score here. At this point, there's actually no risk of them colliding yet. There's no reason to move left. But the reason why B moves left here is because there's this blind spot in the joint action learning. We're now in this unusual position. Again, this is a problem with all these sampling techniques, is you have parts of the state space you haven't sampled enough to get an accurate policy for. So here, what B's learned to do is move into a weird part of the state space where now A moves down, which is bad, because if A moves down here, it's, right? A moves down, B moves up. And now B has found that from this position, it can just move to the right, and A doesn't know how to stop it. Right? So that's where you can always, if you construct this optimal opponent, you can see these weird scenarios. And we can see also, let's see, if A starts with the ball instead, try to make a new episode. So here's a case of A starting with the ball. And again, B wins this game. I'm not sure how, but let's see. A. So what is B doing? I think B here probably just doesn't do anything special, because in order to steal the ball, right, it's going to have to create. So really, when A starts with the ball, it's not that weird. It's kind of the same as what happens with the minimax solution. But once B has the ball, then it starts doing weird stuff which exploit the blind spots of A. Like here, B is moving along the bottom of the field because it knows that A doesn't know how to deal with that, because it's converged to something where it hasn't seen enough of those scenarios. Whereas with the minimax Q opponent, like here you see, when it starts without the ball, it loses every time. Right, and the minimax Q opponent has these, completely even statistics with the reward value, where it just adds up to 0. Now, similarly, I said the independent Q learning. Now, this has some blind spots, right? But it's still like, this is negative 0.2, the actual value. But there is some positive win rate here. There's some parts of this policy are actually following the minimax policy. The independent Q learning, right? This is the one that we learned that doesn't use any game theory. This is just learning, and we hope it converges, but there's no real reason why this should converge. And here we can see that the policy it's learned, even though it did really well against the random opponent, and it even did well against the minimax opponent, when we train an optimal opponent, it loses 100% of the time with a really bad, like this is almost as bad as the outcome exploiting the random opponent. So this IQL opponent is just as exploitable as the random opponent. And actually, it's exploitable in a way that's a little different, because we're able to guarantee a win. And we can see an example of how it works, but here B is the optimal opponent. So here, B is going to try to score, but then because B is trying to, move and score, and there's a chance of it losing the ball. So that can happen. However, once A has the ball, what B does is B positions itself right here. And because A has a deterministic policy, right, B has learned that A from this position will always move up. So what B is going to do is attempt to steal the ball by moving into A. And sometimes it will fail. So in this case, it failed. But B is just going to stay still now because it knows A is going to move down again. And then it just tries this again. And it will just repeat this over and over again until it successfully steals the ball and then can score. So that's the reason why the optimal opponent can never lose to the IQL opponent, because it has a deterministic policy. And in all these stochastic games, if you have a deterministic policy, there is always a way to exploit it like this, where you can never lose and you get the most reward, right? If we compare it to the minimax policy, right, A, instead of moving down, and the difference in the minimax policy is A does move down, right, with this probability, but there's also a probability of A staying still. And that creates a situation where B can't guarantee this scenario where it can just repeat the stealing opportunity over and over again. Yeah, so can't exploit it as well. So, okay, any questions about the optimal opponents and the flaws of independent Q learning? Okay, well, I have one more thing I was going to talk about today, which is the same kind of joint action learning we talked about, but there's another way of doing it, which is a little bit easier. It's computationally faster. We talked about when we were doing normal joint action learning, we learned these action values here, and then we applied some equilibrium solution concept like minimax to solve this. And if we have an equilibrium solution that we can compute, like minimax, then this works. Although we do have to solve a linear program. It's a little bit involved. There is an alternative thing we can do with joint action values, and that is we can try to simultaneously model the policies of the other agents. Now, there's a reason we would try to do this. And the reason is if we have the joint action values and we actually know what the other agent's policies are, then from each agent's perspective, we can compute this best response policy to the other agents, whatever their current policies are. And this, in this case, this is showing it with R for a normal form game. If this was a stochastic game, these R values would just be replaced with the Q values that we learn, that also are learning the future, the impact of future rewards on the game and future transitions. So now we can compute this argmax here, and we don't need to apply the game theory solution concept because we're just gonna, because we have these estimates of what the other policies are. And one way we can learn what the other policies are is we can just count the observed actions for the other agents and just average them, right? Average the count of actions in a given state. Right? This is showing it for a normal form game where there's only one state. But if we look at it right here for a stochastic game, we would have a model, these counts for every state, and then we try to average these estimates. And then we have the same joint action values, but now instead of that value function where we compute the equilibrium solution, now we just have to calculate the maximum, and for the policy choice, we have to do the argmax of this thing. And this thing is just computing the action values for one agent. So its own action values, just like we'd have in single agent RL, but making use of the joint action values and the policies for the other agents, or the current model we have of their policies. So this calculation means we can avoid calculating the game theory solution concept, which we might not even be able to do in the case of like Nash, Q learning. We might not have an easy way of computing it. But the nice thing about this is that, let's see, what do they say with the convergence properties are. Oh, well, I have it written down here. So if this algorithm converges, where the actions like this argmax, using the values, right, where these actions eventually converge, that means that we have found a Nash equilibrium, right, if it converges. Also, if we're in a Nash equilibrium, then everything will remain in a Nash equilibrium for subsequent episodes. So that's nice. We don't have to worry about losing it. Now, it's possible, like this is says argmax, right? So this is also not able to learn probabilistic equilibria explicitly here. Because whenever an action is selected, it's going to use this argmax. It's not going to like calculate like a minimax probabilistic equilibrium. However, as the learning process evolves over time, these argmaxes will change, and that will produce an empirical distribution of the actions. And that distribution could converge, even if the individual action selections don't converge. And if that happens, then the empirical distribution is a Nash equilibrium for the game. And the joint action values also are the Nash equilibrium values. And we also know that this converges in several game classes, including two-agent zero-sum games. And I'm sure, so there's other general sum games where this also works. So that's nice. We can try to apply it. So here's an example of it for zero-sum games, where again, we're computing, right? This is taking the other agent's policies and then computing the Q values, although here it's just computing them, this is computing it for a single action for the agent. This is computing it and returning just the argmax for it, which is what we need for this algorithm. Right, we need to go through and compute these, and we just need to figure out which action for our one agent that we're concerned about maximizes this. So we can also do this for general sum games. It just involves looping through more, the other agents' actions. But the other techniques we had, right, prior to this agent modeling, right, because here, this we can apply to any stochastic game. Now, it might not converge. That could be a problem. But we can apply this algorithm to any stochastic game. This algorithm we had earlier, we have to have a way of computing this value thing. And this is an equilibrium solution for this. And this we might not be able to compute. So I only had a version of it that works for the zero-sum stochastic games. Because the other equilibrium are hard to compute, or we don't know how to compute them, or it's an NP hard problem. But for algorithm 8, we don't have to worry about that. So that's good. We can apply it to other things, other games. So I'm going to show an example of it. So the soccer game is a zero-sum game. So it's one of the games where we know it does converge. There are more, maybe the actual like parameters you have to use to get it to converge are a little finicky. So here I'm running it, and we can see it hasn't, it is getting stuck with this certain, non-zero value here for the agent playing against itself. And we can see that it's also not that great against the minimax opponent. Like, so its convergence properties are a lot more finicky than something like independent Q learning that may not converge, or the policies could alternate or something. This has better, theoretical guarantees, but the actual, practically getting the convergence could be hard. And then also, if we train an optimal opponent against this, we can see, it is still exploitable, just like we'd expect for anything that relies on sampling, because it's not going to learn an exact solution. Because we can apply this to general sum games, we can also look at that level-based foraging example we had before. This was the environment where, this task where we had agents, like these are two agents and there's two items and they're trying to collect an item, but they can only collect an item where they have a level, like their levels add up to the item level. So we had solved this in a previous chapter, and this had an exact solution where the first agent collects this item, and then they go together and converge on the second item and collect it. So this had a solution where it was like 14 steps was the time required to solve this as best as possible. And then we also looked at different ways of solving it with sampling. So we had central Q-learning, independent Q-learning. This is a problem that's cooperative. So the solution doesn't actually need a game theory solution to work. We can just try to optimize the sum of the agent rewards where they're cooperating. And that's why this central Q-learning worked, where we just take the environment and we reduce it to a single agent RL problem, where we have this scalar reward transformation where we take the two agent rewards, sum them together, then we get a single reward value, and then we can apply normal RL algorithms. But this is showing it for central Q-learning, independent Q-learning, and the actual game theory solution, which in my case, applying this algorithm, in my case, it actually has worse convergence than the other ones. I mean, none of these are finding the exact solution, right? This is slightly worse in terms of the number of steps than the exact solution, but it's still converging pretty quickly. In the book, they have this similar chart. Here I'm showing the number of steps to complete the episode. In the book, they show the reward value, so the numbers go up instead of down. But here they were showing how the agent modeling version actually converges faster and learns better. But again, it's like here they say they decay the exploration rate from this to this, and they have this learning rate, and who knows, the details of the implementation probably matter a lot and how well these things converge. Tweaking the parameters of these other algorithms, can make them work a lot better. They show central Q-learning consistently performing worse than the others. I didn't find that when I tested this out, where the central Q-learning actually did fine the way I did it, but who knows? Conceptually, all of these should work to some extent for the level-based foraging game. And then we can also apply this to the rock, paper, scissors game, in which case, so here it's a little less clean than what they show in the book, because the book is showing this example with fictitious play, and fictitious play doesn't have a state. So you from the very beginning, you can take the reward values you get and assume those are all that matter. When we do joint action learning with agent modeling, we do have multiple states. And here you could see how these joint action values, it did learn the proper values for the game, right? But initially these values are wrong. And because it has to actually converge these joint action values, whereas if we know for sure that the game only has one state, then we can just immediately start using the the reward values for the best response, right? Eventually, when we do the full algorithm, when we calculate the best response, we have to use the Q values, which we have to wait to converge. That's why this doesn't look quite as clean, but we can see the same kind of triangular trajectories where it's showing the probabilities for each agent, the empirical probability of the actions. So this is a case where on any given step, the action selection is going to be one of the rock, paper, scissors with whichever the argmax is. But if we average this over time throughout the learning process, they continually alternate in such a way that the empirical distribution ends up being close to 1/3 each time. This is what it's converged to. So it hasn't quite converged yet. But we can see that the values are approaching this 1/3 value. But so this is a case, this rock, paper, scissors game, where if we look at the convergence guarantees, right, this would be under these last two bullet points, where the actions are not going to converge, but the empirical distribution will converge. And because it's converging, we know that whatever it's converging to is a Nash equilibrium, because that is the only thing, that is the only empirical distribution that would actually produce convergence. Anything else would end up diverging over time. So that concludes the discussion of agent modeling. There is this discussion of Bayesian information and other, this is like alternatives we could use to model the other agents, other than just this simple averaging over time that accounts for uncertainty. So next time, We can maybe talk about that, and then move on to different algorithms that end up doing policy-based learning instead of what we've done so far, which relies on the joint action values entirely, right, for deriving the policy, or a combination of them and some empirically measured policy. But next time we'll look at algorithms that they get past some of the limitations of joint action learning by explicitly trying to learn the policy, which also fixes the problem we had before with this pathological example where we have a stochastic game where the joint action values are not sufficient to learn the probabilistic equilibrium, right? So yeah, the policy-based learning will avoid some of those problems. So before we finish, any questions about anything we talked about today, or anything anyone wants to bring up for next time? Yeah, so we covered through section 6.3.2.